G'day, welcome back. This episode I'm going to look at reaction forces, in particular normal reaction forces. I'm going to have a look at how you can calculate the value of these forces and also try and explain what brings these forces about. So let's have a look at the situation you're probably in right now. I know I am. Sitting in a chair. And in this situation we're going to consider a couple of Newton's laws. Now his first law says that an object will remain in a constant state of motion or non-motion until acted upon by some other force. And his second law says that every action has an equal and opposite reaction. So let's have a look at the forces that we know are existing in this situation. We know that there is a weight force acting down. The weight of the body, my body, is pushing down on the chair. Now if that was the only force acting on me, I would continue to move down, because that would be an unbalanced force. Because I'm not moving down, there must be another force, equal in magnitude but opposite in direction, acting up. Now that force that is acting against my weight force is called the reaction force. Most people just accept that. We know it exists because there is no movement up or down. But what causes it to occur? The chair doesn't have a consciousness, and as you sit down, think, oh, I have to push up a bit harder now. So there must be some other explanation as to what causes it. So just imagine that the atoms in my bum and the atoms in the seat were represented by these little spheres that I've got on the screen. And each of those atoms we know has a positive nucleus surrounded by a negative electron cloud. We know that my body will be exerting a weight force down due to the masses of all those atoms that are in my body and the acceleration due to gravity. We also know that there will be a weak electrostatic repulsive force up, pushing my body and the seat apart, because around each of the atoms in the seat and each of the atoms in my body is a negative charge, and those similar charges will repel. Now at this point, that electrostatic repulsive force is very weak, because the distance between me and the chair is quite large. As I move down due to the fact that there is a larger downward force than upward force, so I can move down toward the seat. As I move down, my weight force will remain the same because I'm not gaining any mass, but the electrostatic repulsive force will increase because the distance between the electron clouds is now getting less. You get to a point where there are equal and opposite forces, and at that point there, you are basically floating above the chair. The reaction force is that electrostatic repulsive force. So it comes about not due to consciousness of the chair, but due to the fact that the electron clouds in the atoms in the chair repel the electron clouds in the atoms in my body. Let's have a look at a typical physics classroom situation, a wooden block on a wooden plank. Now the wooden block has a mass, so therefore it will have a weight force down. And we've just said that there's going to be a reaction force up. Because the weight force acts directly down, the reaction force will be directly up. And in physics we call any force which is perpendicular to an object, we call it the normal force. If we then tilt this plank, we'll find that the block will still remain in position. It doesn't start sliding. It has a weight force acting down, but we can actually look at two components of that weight force. We can consider one component acting straight down the incline, parallel to the incline, and another component at right angles or normal to the incline. Let's have a look at each of these components in turn. First of all, we'll look at the normal component. Now we know that that normal component will experience a normal reaction force, which will be equal and opposite to the normal weight component. If we then consider the force parallel to the plane of the weight, and we will then say, why is the mass not sliding down the plane? The reason is there is a limiting friction. If that limiting friction is not greater than the component of the weight force down the incline, then the thing will not move. In fact, if we look at all of the forces in this situation, the weight force being resolved into its components, the normal reaction and the friction force, we'll see that they're totally balanced. Because there's no net force acting on the object, there is no change in motion. Let's tilt the incline a little bit more. If we raise it up a little bit more, we'll notice that the component that is parallel to the incline will increase, and the component which is normal to the incline will decrease. Now, if that component parallel to the plane is slightly larger than the limiting friction, then the object will begin to move. It'll begin to move because it now has an unbalanced force acting on it. Newton's second law says that force equals mass times acceleration. So if there's an unbalanced force acting on a mass, it will begin to accelerate. It'll begin to change its motion. Let's have a look at how we can calculate the values of these components. If we look at some angles, we look at the fact that the weight force straight down is perpendicular to the ground level. If we call the angle between the incline and the ground level theta, the third remaining angle in that triangle is going to be 90 take theta. And because we know the angle between the force parallel to the plane and the force component normal to the plane is 90 degrees, therefore the angle between the weight and the normal weight component is theta degrees. If we move the force parallel to the plane down to make a vector triangle, we can then use that and some geometry and trigonometry to help us work out the magnitude of these components. So let's just simplify the diagram and get rid of all those bits, and now just magnify it a little bit. We know the weight force down is equivalent to mg. Now we've just determined the top angle is theta degrees. So the component which was normal to the incline is going to be equivalent to mg cos theta, and the component which is parallel to the incline will be equivalent to mg sin theta. Now throughout this year's work you're going to have to be very familiar with the geometry and trigonometry which I just went through there. We're going to have to apply that to many different situations.